Our next presentation is going to be given by Dr. Scott Glenn. Scott is at the Institute of Marine and Coastal Sciences at Rutgers University in New Brunswick, New Jersey. He's a professor of marine and coastal sciences at Rutgers. Received his doctoral degree in ocean engineering from MIT, the joint program with the Woods Hole Oceanographic Institute. In 1983, he worked first at Shell Oil for 4 years. That's Shell Oil, not BP. As an ocean wave and current forecaster, and then at Harvard University for another 4 years as a Gulf Stream forecaster for the U.S. Navy. For the past 20 years, he's been at Rutgers University, where he's an active educator at that university and nationally. He is co-director of the Rutgers University Coastal Ocean Observation Laboratory, a global distributed collaboratory for ocean sciences. Scott?
Oh, thank you. Okay, down to 28 minutes. Here we have the Mid-Atlantic Bight. I'm going to talk about building this regional ocean observatory in this 1,000-kilometer reach of coastline running from Cape Hatteras to Cape Cod. You'll see this as a very wide continental shelf and lots of rivers flowing onto the shelf. So the questions are, what are the interactions that are taking place on this wide shelf, and how does that impact the ecosystem? The outline for today's talk, first I'll talk about the science-based build-out of that network and how the power of peer review really did develop a very modern network, but there are challenges then of expansion to the national scale. We'll talk about service to society and how these ocean observatories, originally built for science, are very capable of multi-use activities. How, in the process, we've transformed ocean education, where we've broadened the definition of an oceanographer, and then we're looking at the broader impact of education. We often hear about the broader impact of our science. We are now seeing feedbacks between what we do in education on science and society, in particular the Gulf oil spill. And so this is the area that we're working, large marine ecosystem number 7, the northeast U.S. continental shelf. There's 64 of these worldwide. They have a lot of the fish. So these are very productive regions, but it's also where the people are. If you look, we are probably one of the most highly urbanized coastal regions in the U.S., so there's a lot of rivers and things going into the water, coming onto this coast. It is also the hub for marine transportation. So there's a lot of multi-use aspects of it. If we look at the sea surface temperature difference, summer to winter, globally, there's a couple of hot spots that light up. One of them is right here. So we have a very large temperature change over the seasons from winter to summer. And as a result, the fish species in this area are very migratory. Here we've tagged a bunch of fish right here in New Jersey, and we see them migrate back and forth over the season, over the year. We also see that there is large trends in temperature. Here, if we look at the fall bottom temperature in this area, 1997 through 2008, 5 degrees C changes, very large changes in temperature. You don't see that at the surface. This isn't just warming. This is regime shifts in the circulation that are causing this. And so this is then going to impact these very highly temperature-dependent fish. Why is this important to do now? Well, there's a growing human population. And as we see, we're somewhere here around 5-6 billion right now. We're going to be growing to 9-10 billion, and most of that is in the less developed countries. These are those less developed countries where that activity, where most of that growth in population will be. That's where we need to feed these people. If we look at the fish populations, those are being reduced. So human population grows, fish population is being depleted. These are the regions where it's being depleted the fastest, and all that fishing activity is being displaced to the less developed countries. So this is a difficult situation that we're putting ourselves into. So to better understand this, we have to better understand our large marine ecosystems. And the thing that's stopping us the most, the thing that we lack The most in this understanding is our inability to maintain a sustained presence at sea so that we can understand what's going on. We can put buoys out at sea. They sample well in time, but not in space. We can send ships out, and they can sample well in space, but they're too expensive to keep out for long periods. And so what do? If you ask Walter Monk to look back on how we've traditionally done oceanography, and he characterizes it as a century of undersampling. If you look forward, Walter was asked to do this in 2000 and comment on the advent of satellites in oceanography, and he came up with the 1 + 1 = 3 scenario. When you take satellites in space, you can look down at the ocean and see the vast distribution of the surface properties with satellites. And if you combine that with subsurface ocean arrays to get what's below the surface, here you sample in the horizontal at the surface, and in the vertical below that, you combine them into the 1 + 1 = 3 scenario for a well-sampled ocean. The way we do that globally is passive imagers that we put on satellites that tell us temperature distributions and phytoplankton distributions from ocean color, and then we put active radars on satellites that give us the currents. So what's in the water and where are those properties being transported to? The other thing is that we use these vertical profilers, the Argo network, 3,000 of those globally distributed to get the vertical distribution of properties in the ocean. So that's the 1 + 1 = 3 on the global scale. The large marine ecosystems are on the coasts. How do we accomplish that? How do we turn this global network into something that we could use in coastal regions around the world? I don't think we would have ever met that challenge if it wasn't for the National Ocean Partnership Program. NOP has these strategic goals here. One is to sustain this integrated ocean observing system, IOOS. That's one of the main sponsors of the work that we're doing here. Promote lifelong education, modernize the ocean infrastructure, and technology development. We are technology limited in our ability to sustain a presence at sea. And so we want to modernize that and then foster these interagency partnerships. There's no one agency that can go out there and do all the work in the ocean. It is so undersampled. So we have to combine our efforts, and by combining these research efforts, they're compounded through collaboration, coordination, and cooperation. That was what 10 years of the NOP program has shown us, that we can do more if we collaborate, and now it's time to take these partnering skills and apply them to society's needs with haste and vigor. And so that's what we're going to do. Here's the observatory that we built for the Mid-Atlantic Bight to apply that 1 + 1 = 3 scenario. We do have satellites in space that we pull the data down from with our own local dishes. Here we've built a shore-based radar network. So now instead of looking at ocean currents from space, we look at them from shore. And instead of putting drifters out in the ocean, you can't drift out of the ocean. If you put a drifter in, you're always going to be somewhere in the ocean. But you can drift out of a coastal area. And so you have to have some means of propulsion to stay within that coastal area. All this feeds ocean models, and all of it is supported by many, many agencies. So this is in the NOP tradition of collaborating and building that 1 + 1 = 3 scenario. Here's some of the examples of those technologies. So we start off with that. Here's the global scale that we've seen before. We downscale to the regional and to the local scales now, where we can go in right up into the rivers and use that same remote sensing data from not only the U.S. but also different countries. So we have more and more times that we can see river plumes during a normal day. So satellites in space tell us what's in the water. Satellites, they can be applied, downscaled to the regional and the local areas. Now we need the currents. The altimeters have very coarse resolution over here, but the radars on the beach, all these different technologies can give us now the regional scale, and again, downscaled into the estuaries, so you can see the rivers coming out onto the shelf. Last are the underwater vehicles, the gliders. I have a few slides on those because this is a newer technology where there's no propeller on these vehicles. They're buoyancy driven. They pull water in and out of the nose and move up and down by changing their buoyancy and have wings so that they fly forward. They move very slowly through the ocean, but they can maintain positions or traverse large areas. This is the anatomy of the glider. In the front is their buoyancy pump. That's the engine that moves it back and forth. In the tail is all the communications. And in the middle is the science payload bay. So if it fits in there, it flies. Anything that you want to put in the water can be flown. They start at the surface. They pull water in, about a cup of water. It sinks down, moves down to the bottom, pushes that back out, goes up and down through the water column like that, comes up here, resurfaces, pushes the tail out of the water, phones home, checks its GPS, sends its data, see if it has any email, and goes on about its business after that. And so we can autonomously control those from that control center. We have a fleet of over about 20 of these things. Anything that fits in that payload bay. So there's a couple of dozen different things that we've put in there. They can be flown, different technologies adapted for different applications, and flown anywhere in the world. So they give us that global ability to fly sensors and maintain them below the remote sensing data and provide that 1 + 1 = 3 scenario. Here's how we've implemented a lot of this. We've done it through science experiments, starting here near our coast. We'll go through these and show how we've built these collaboratories, first co-located down here with the science, then moved to on campus, and then a virtual collaboratory. Now, anywhere you have Wi-Fi access and coffee, all you have to do is take this computer and you can run that entire observatory from your laptop. So here's quickly, we'll go through, here's along the coast. We want to look at these recurrent regions of hypoxia along our coast. We see, well, there's rivers flowing into some of those. They bring nutrients, phytoplankton blooms, they die, decay, they use up the oxygen. Well, some of these don't have rivers, and some of them have very major rivers. Why are they located? We see bumps in the topography. So we'll deal with those first. Here, we look at the sea surface temperature maps, locally generated. We see upwelling centers, cold water near the beach. We drive across those upwelling centers with ships, and we see there's a characteristic structure here in the upwelling, these two bubbles. And so what is that structure? We want to better understand that. We use models to understand it. Here we have warm water at the top, cold water at the bottom, 3 bumps in the topography. We blow the wind, and we see upwelling centers develop that have downstream of those bumps. We see that same structure in the model as we see in the data, and now we see eddies. Eddies are developing in our ocean, and we see that in the data. We blow that data up. Here, now we look at the sea surface temperature with the radar-derived currents, and we see an eddy in the region. We drive ships out into this eddy around the cold water. We see subsurface rivers of phytoplankton being advected, circulated, and incubating in these regions, in these eddies. They die, decay, and they use up the oxygen. So we've developed ways to figure out these 3 centers. What about this one? There's no bump in the topography there. Here was the NSF Hudson River Plume experiment, where we looked at the river plume during downwelling and upwelling winds. Here it's going along the coast. Here it's moving out into the ocean. We expected a very simple textbook answer, and we found out our textbooks weren't as good as we thought. Here we see the plume coming out. It comes out as a squirt, very fresh water with the tide. It comes out as a tidal bore. You can see it. Here's the ship's salinity record as it gets hit. You can feel it shudder the ship as that plume comes out. And we see the radar showing us the structure of that plume. We put dye in it. We put buoys in it and see what it does. And we see recirculation zones form in the radars. We see it in the buoys. We see it incubating large phytoplankton. Look at the water there. That's not the blue water that we see offshore in the river. And again, the oxygen drops. So there's features out there that are accumulating and serving as incubators. We now look at where that river water goes offshore. Here's an example of one of the sea surface temperature maps where, hey, it doesn't look like it's going along the coast. It looks like it's following the ancient riverbed through the Hudson Shelf Canyon, Hudson Shelf Valley and Canyon offshore. But no scientist would ever believe that just a sea surface temperature is enough to move their boat. So we see in the radar, we see the currents that are going along there. Well, still we're studying this with a boat along shore. Boats are expensive. We see remote sensing data, but is it enough to move a boat? So we send in a robot. We have a robot with the same CTD as they have on the boats. It flies out in the middle and it finds the same fresh water that's offshore. The scientists can no longer deny it. They take their expensive boat, move it offshore, and here in this cross-shelf line, here's the plume that they had been studying. They move it into this plume, and it's even bigger. So there's even more water being transported offshore from this river. And this was one of the most interesting discoveries of this whole project. Why is it not following the textbook case along the coast? This moves us into one of the most collaborative experiments we had on here in this area, Shallow Water 06 on the outer shelf now, where we had 7 ships, UNOLS vessels, gliders, aircraft, 62 moorings, more than Woods Hole's ever put in their life. All these satellites being all focused on this one area where we're going to study, all with centers analyzing data, communicating to the ships to get them in the right spot at the right time. What was going on shore? Up in Albany, just before that experiment started, we had the wettest June on record since 1795. We had a lot of rainfall in Albany. By the end of July, by the end of June, we see that it's all that water from the watershed is moving down here past New York City, past the gauging stations. Where does it go from there? Does it get out to our researchers are working in that area? If we look at those radar vectors, now at the shelf scale, we see that the dominant winds from the southwest result in this characteristic U-shaped current on our shelf. And if we look at the winds we experienced during that experiment, here's the buoy that's offshore. Most of the winds are the southwest. We see that U-shape in the currents. We deploy virtual drifters in the radar field, and we see all the waters going right through our study site. If we fly gliders across the shelf through this region, we see very fresh water, some of the freshest water that we've ever seen in the last decade out there. And so here, this was nicknamed the Albany Puddle. It's extreme stratification at the shelf break. This rainfall all up in this region went down through the river, ended up in our experiment at the outer shelf. So it's all connected. So we've developed all these technologies. What do we do? How do we apply them to societal needs? That's where the NOAA IUS network comes in, and I'm going to talk about 2 of the applications, safety at sea and ecosystem decision support for fisheries. First, maritime safety for search and rescue. If we have these vectors, how can we test them? How can we use them to see if they'll improve our search and rescue? Here's 2 examples that were done early on where we put a drifter, these are one of the drifters that the Coast Guard uses, in the water, and it follows this black line. If you use the existing technologies that they had at that time, that's the red line. They would look for you here. And if you use the radars that we have in place, they would look for you there. And just here's another example. If you have the radar, they look for you there, and here, if you don't, they look in the wrong spot. And so this is life and death. If they look for you here, you die, and if they look for you here, you live. And that's a good enough reason to invest in a national network. And so we then went through the process of testing and evaluation of all this. We know that we can't use local data. That wasn't doing any good, so they were trying to use ocean models and the radars. They evaluated HICOM, one of the best models, model that I use every day, and they ended up with a low confidence rating for it, and with HF radar, a high confidence rating. And so we developed then a test case where we put 5,000 particles into a test scenario with real drifters out there, and evaluated these 2 models based on the random flight characteristics of that network of drifters. And here's the examples. 24 hours into the search, here's the 5,000 drifters, all with different random flight characteristics based on low confidence and high confidence. And there's the actual drifter. So we see that HICOM is starting to drift away from the drifter where the radars are staying with it. And we'll go through time, 48 hours. We see this 72, 96. HICOM, this is where they say they should search for you. It's not very good if you are going to be living, or if you're down there. And here, the HF radar kept up with the system. If you look at the search areas after 96 hours, you see a reduction in 3 in the search area, much more likely to find you. And here, you're only saved because the SAR ops can't draw an ellipse. It has to draw a box, and you were down there in the corner of the box. So after this evaluation, the radars were made operational by NOAA and the U.S. Coast Guard. It made it to the very top page of the Department of Commerce, displacing the new secretary being sworn in. The idea now is to take, now that we've done this for the Mid-Atlantic, set it up for other regions nationwide. The other example that we have is for ecosystem-based management, where you take all these data and layer them together with the glider fleets, the satellite imagery. Here's those HF radar currents in between the altimeter tracks. You can see how much better resolution we have on the shelf. You assimilate that into models, and then you use all that data to map onto the fisheries data that we have collected on a normal basis. And we'll show some of the analysis from the fisheries folks of those combined data sets. And here, typically they would use bottom roughness, some kind of estimate of the bottom roughness to look at the habitat. And you see that, well, these things like rough bottoms, these flounder. And they also like certain temperatures of water. So here's bottom temperature. And so, okay, so they're cold-blooded. They care about the temperature of the water. One new thing they found that they also like to eat. And so they find that by looking at the surface currents from the radars, that they like places where there's upwelling. So yes, there's more of them where there's upwelling, strong upwelling. And the other is the different chlorophyll products. And so there's places where they like the chlorophyll. And so you combine these areas and you find different spots that they say are sticky to fish. Where do the fish want to stick? Where do they want to be? What are those habitats they like? And then, well, for these flounder, we find a few places where they like to spawn like that. These are the places that are sticky. We want to look at the connectivity. How are those places connected? And here again, you use the currents. You put in those drifters. And you look at, okay, if here they're spawning in some of these places, like this one right here, where do their larvae go? These larvae have to get back into the estuaries to live. So as the eggs are spawned in there, they're going to be drifting at the surface. If they were spawning in the winter, they would drift offshore. If they're spawning in that place in the spring, offshore. In the summer, mostly offshore. But in the fall, that's when most of the spawning takes place. They have a lot more chance of coming back into the estuaries. So we find the places that are sticky to fish and then how they're connected by combining the data sets. You combine all that and we see the need for a national HF radar network. Here we have a lot of scientific interest, and so we developed a network. Here there's a lot of scientific interest in these things. Down here in the Gulf, there weren't as many scientists working on it. The radar network's missing, and that's where we have the oil spill, and that's where we need it the most. So how do we expand this? Well, we've developed a plan for NOAA to do that. We already have 129 sites in it. More regions are coming online, and a 5-year build-out. Search and rescue is the driver. You know, saving lives is still a good thing, but all the others will benefit. So now in education. Here's our Transatlantic glider mission. This was a challenge to us in 2006. Rick Spinrad, after seeing these gliders in action, said, take one of your gliders, modify it, and fly it across the Atlantic, inspiring students along the way. He only had one line to say, here's all the things that we had to do to accomplish that. And so there's all kinds of improvements in glider technology, most of them going like 30 days to 300 days, a factor of 10 in endurance. We had to figure out how we path plan. How do we get all these data sets into some interface to decide how we fly across, and where do we get the human resources to do it? Well, here we went to our education programs. We can't do this as scientists, but we can do it as education. And so we went to our COSI network, these are NSF projects, where we had this networked ocean world, and they build these places where these collaborative workspaces online. How do we get people all over the world to collaborate for science or education? Well, we're going to use some of those activities here. We went to our young people, our students, both at Rutgers and abroad, brought them together, and are building this young international community. And so this challenge is being taken up by undergraduates. We've had several long-duration educational flights. RU-15 here, where we left New Jersey to Halifax on our first test run. RU-17 almost to the Azores. RU-27 all the way across Drake and the thermal glider Cook. And so we've had several glider activities going on, all education-based. All the students building and running and operating the systems. And we'll just highlight RU-27 as it goes across. Here, it's being picked up by the Spanish on December 4th, brought home to Bayona. Bayona is the place where the Pinta arrived with the first news of the New World. It got a hero's welcome, and here's all the kids. All the senior people backed away and let the kids go there. These are the kids that were into schools that wrote letters that were put inside the glider and flown across over these 221 days, really inspiring that international collaboration. The whole thing was documented from using English majors to document the work of the marine science majors. And so even though we were working, in an observatory, sometimes it seemed like we were on a sound stage with all the cameras that were going to keep all these activities alive. The last thing I'm going to say is that, we built all those systems. Are they being used for anything else? Here, the Gulf oil spill. That collaborative portal that we used to organize all of our activities is now being used to organize all the IUS activities in response to the Gulf oil spill. So education, feeding back on the spill. All the different blogs, this is our interactive sites that we used internationally to coordinate what we're doing, are now being used to coordinate all the different activities of the gliders and radars and other assets that are in the Gulf. All the interfaces that we built in Google Earth for sharing data and overlaying the satellite imagery, the altimetry, the models on the tracks, those are being used in the Gulf. And our next challenge is again, delivered to us by NOAA. Can we take a globally distributed network of scientists and students and repeat the Challenger mission? This is the first international global scale science cruise conducted in the 1870s. Can we do that with gliders flying around the world? And so we started that project with those same portals and same collaborative networks, now using the new thermal gliders. And here, two English students that are making the documentary are deploying the gliders for us. And so we're really broadening the definition of oceanographer. But now it's supporting science. We're flying these gliders across 26.5 north. This is the most important line for the Rapid Climate Change Program. This is where the meridional overturning circulation is greatest. And so we're going to contribute to that for them. So there's my conclusions. We did a science-based build-out, and we expanded science missions to produce the core observatory. The multi-use capabilities have been proven. We're transforming ocean science education, making that broader range of oceanographers, and the feedback of the education is now occurring to science and society. It's being demonstrated where the broader impact of education feeds back. Thank you.